Short-circuiting sea level rise. Greenhouse gases warm the Earth principally in the tropics. Heat migrates from warm to cold, thus tropical heat migrates to the poles where it melts ice caps, contributing to sea level rise. Warming oceans expand, leading to further sea level rise. The deep oceans are an underutilized alternative heat sink with a lower coefficient of thermal expansion than the ocean's surface. The natural state with current atmospheric carbon dioxide levels is oceans 20 meters higher. The principal driver that has and will lead to these levels is meltwater from the ice caps. Tropical storms are the primary means of conveyance for tropical heat to the poles, which are the fastest warming regions of the planet. The oceans, which on average are 4,267 meters deep, range in temperature between 4 and 2 degrees Celsius at depths of 1,000 meters and greater. The sun warms the ocean's surface, which can reach temperatures as high as 30 degrees Celsius, as was the case with Super Typhoon Haiyan, though temperatures of 26 degrees Celsius to a depth of 45 meters are sufficient to form the typical cyclone. Wind and wave action readily mix surface heat to a depth of about 100 meters, but below that it migrates slowly because the natural tendency is for heat to rise. It is estimated it takes about 350 years for surface heat to diffuse naturally to a depth of 1,000 meters. The coefficient of expansion of seawater decreases in the ocean to that depth before starting to increase again, though it never reaches the surface high except for in the deepest trenches. Forcing surface heat to a depth of 1,000 meters replicates and can perpetuate the conditions that are believed to have brought about this current atmospheric warming hiatus, sap the energy of tropical storms, short-circuiting their transport of heat towards the poles, sea level rise and atmospheric warming while minimizing thermal expansion. Heat pipes are the most efficient and rapid way of moving heat from locations where it can do harm to a benign heat sink. This is accomplished through phase changes of a working fluid. As heat is applied to the evaporator region of the pipe, the hot end, the working fluid is vaporized and under pressure transfers rapidly, in some cases near the speed of sound, to the condenser region, the cool end, where the latent heat of condensation is lost to the cold sink as the vapor transforms back to liquid. In an ocean setting, the condensed working fluid is then pumped back to the surface to complete the cycle. The introduction of a turbine and generator into the heat pipe permits the production of mechanical and electrical energy that can be sold at a profit as well as finance the environmental and sea level mitigation functions of the system. The heat pipe overcomes the cost and environmental problems associated with conventional ocean thermal energy conversion systems, which use large pipes with large and costly infrastructures to support them and massive water movements to overcome the inherently low thermodynamic efficiency of a Rankine cycle with small temperature differences between hot and cold heat sinks. Heat pipes can economically short-circuit heat movement from the tropics to the poles to reduce melt-driven sea level rise as well as thermal expansion. The ocean's mass allows for the absorption of a great deal of heat to limited effect, particularly below the thermocline. Estimates are the oceans have the potential to produce between 14 and 25 terawatts of power from ocean thermal energy conversion, whereas the planet currently operates on about 16 terawatts of primary energy, 14 of which is derived from fossil fuels. The community that capitalizes on this opportunity stands to monopolize one of the largest industrial sectors of the global economy. A 2008 OECD study ranking port cities with high exposure and vulnerability to climate extremes rated Vancouver amongst the world's top 20 port cities at risk to storm surge and sea level rise. By 2070, with sea level rise estimated at only half a meter, as much as $303 billion worth of assets will be at risk, while the combined risk to the remaining 135 cities studied approaches $33 trillion. It is only natural to want to mitigate this kind of risk, and this can be done with local technology that can be marketed to the world. British Columbia has the intellectual resources, the mining, energy, and shipbuilding expertise, plus the resources necessary to garner a significant share of the multi-trillion-dollar per year clean energy market. By effectively addressing sea level rise and climate change, The province safeguards and preserves its forest, fishing, and tourism legacies, and with a viable fossil fuel alternative can counter the influences pressing for the movement of coal and bitumen through our territory and along our coast. Let October 19th be the moment the planet begins to heal and the rise of the oceans truly does begin to decline.